And welcome to the first week of Chemistry 212, Organic Chemistry. In this class, we're going to be learning a lot more about the way reactions happen, and in particular, how bonds break and how new bonds are formed. So we're going to be taking a lot closer look than we have in the past about the nature of bonds. And we're also going to apply that to the many organic reactions that occur that are important in pharmaceuticals, in biochemistry, and in biology, and in other places. Most of that application will happen once you've moved on to Chem 213. Before we start, it's important to review what you've learned in general chemistry. Not all of it will be useful, but well, all of it will be useful to some extent. There are certain parts that will be useful more than others, and those will mostly involve drawing Lewis structures and understanding the way in which bonding occurs by both the valence bond theory and the molecular orbital theory, understanding the geometries of molecules and their intermolecular forces. So this chapter 1 will be a series of 2 short videos in which I briefly cover what you've learned in your previous chemistry courses. So let's begin. First of all, you're going to be covering all of chapter 1 here, and so we're going to go through each of the different sections in your textbook. This lecture will follow very closely with the order and the format of your textbook, so it'll be easy to follow along when you're reading as well. So in chemistry, in organic chemistry, we're going to be focusing on the carbon atom. So the carbon atom is basically the backbone of most organic structures. We're also going to specifically look at what happens to a molecule during a reaction. A chemical reaction will generally occur due to the collision, of 2 molecules. Certain bonds will break, other new bonds will be formed, and we want to talk about why reactions occur so we can predict what the products of an organic reaction will be. And the focus is going to be on the electrons. Where are the lone pairs? Where are the bonding electrons? And that's why Lewis structures will be so very important. So in the mid-1800s, it was discovered that structures were not only specific to what atoms were in them, but all the way also those atoms were arranged and which atoms were chemically bonded to which other atoms. And so you can see on the bottom 2 so-called isomers, dimethyl ether and ethanol. And they're called isomers because the word isomer means that they have the same atoms, but they're bonded in a different way. You can see they both have 2 carbon atoms, 6 hydrogen atoms, and 1 oxygen atom. One thing you'll notice too is this structure is written in the organic way. So generally, when you would write these in general chemistry, you would include 2 lone pairs on each oxygen. And the oxygen would have 2 lone pairs and 2 bonded atoms. And what you're going to see as we move forward in organic chemistry is that often you'll be expected to know that the lone pairs are there, even if they are not written. And there will be simpler ways to do that because we're not going to be dealing with every single atom on the periodic table all the time. Carbon, oxygen, hydrogen, these are the most common. Also nitrogen, sometimes phosphorus and sulfur, occasionally metal atoms, but mostly carbon, oxygen, hydrogen, nitrogen, and those elements, the non-metals, what will be involved. So in the past, we drew Lewis structures by counting up all the lone pairs and bonding the atoms and finally putting the lone pairs in their place. The way we're going to handle Lewis structures will be a little bit different in OChem class. We'll have shortcuts, and the biggest shortcut is just to remember what is the most common number of bonds that a particular type of atom will make. Carbon will generally make 4 bonds. We say that it is tetravalent. Nitrogen will generally form 3 bonds, and we'll have a lone pair here, which again is often not written. Oxygen will generally involve 2 bonds, or will generally be involved in 2 bonds, but also there will generally be two lone pairs on the oxygen atom. It's so-called divalent, the nitrogen being called trivalent. Finally, there are monovalent species such as hydrogen atom, which can only make one bond with no lone pairs, and halides, which again they make one bond and generally have three lone pairs, which again may not be written in an organic structure because it will be assumed that you understand that this is true. And so this is the kind of shortcut that we're going to use for drawing Lewis structures in organic chemistry. So why does a covalent bond happen? A covalent bond happens because two electrons are shared between two nuclei, and those help to glue the positive nuclei together. So you can see two separate atoms drawn here, each with its one lone pair. We can tell hydrogen has one lone pair because it's in group 1 of the periodic table. Remember, the number of electrons, valence electrons in an atom is equal to its group number in the periodic table. When those electrons are shared, two electrons between two hydrogen atoms, you make a covalent bond here. And there's a certain distance between the atoms, which for hydrogen atoms, the distance between their center of their nuclei being 0.74 angstroms. By the way, an angstrom is another way of saying times 10 to the minus 10 meters. It's, proper distance for bond lengths generally. And so we can see that once the electrons and the nuclei have arrived at this difference, this is the lowest in potential energy, and so they'll tend to average around here. Of course, bonds are always wiggling and wobbling, so it will sometimes be longer, sometimes be shorter, but this is what's referred to as the bond distance in between two atoms here, internuclear distance. So what are the forces that are keeping this molecule at this length? Well, it's because the nuclei in the hydrogen are positive, they're repelling one another, so that keeps them from getting too close. But the electrons that are forming the bond are negative, and so they're attracted to both of the nuclei, which helps to hold them together. So how do we count the valence electrons? Again, the number of valence electrons on an atom, or the electrons that can participate in bonding, is equal to the A group number on the periodic table. So that's the kind of group you describe where you skip the transition metals. So I would call this group 1 here, where hydrogen is. Here is group 2, and then here we got group 3, starting up with boron, skipping the transition metals in the middle. Group 4 is carbon. Group 5 is nitrogen, group 6 is oxygen, group 7 is fluorine, and group 8 starts with helium, and all of those all the way down. And so this group number is equal to the number of valence electrons. So when we're going to draw a Lewis structure, the way you would have done it in the past is you would have gotten your atoms. Let's say we're doing NH3. You would have had nitrogen, and you say, oh, this is group 5. It has 5 valence electrons. There they are. And hydrogen, it is group 1, so it has 1 valence electron, and there are 3 of those. And then you would say, okay, I'm going to put the nitrogen in the middle because hydrogen can only make one bond, so it has to go on the outside. Oh, sorry, my cat is here. Sorry, Char, I'm busy. We would then make bonds here to the nitrogen. So if we were in G-Chem, we'd say, okay, we got a nitrogen. We're going to make a skeleton structure. And we'll say, well, out of our total valence electrons was 5 for, equals 1 times 5. 5 for the nitrogen, we have one of those, plus 3 times 1 for the hydrogen for a total of 8. And then we would draw a skeleton structure where we put the hydrogens on the outside because they can only have 2 electrons. They're special. Remember, hydrogens can only make one bond. That's something special about hydrogen. No lone pairs. Finally, we put the last 2 electrons on the nitrogen. That's the way you do it in G-Chem. In O-Chem, it's important to just kind of go back and think about how many bonds that the nitrogen want to make. And so memorizing this right here, going back a few slides, memorizing this, that carbon makes 4 bonds, nitrogen makes 3, oxygen makes 2, and hydrogen and halides make 1, is very important for OChem. It will make things easier. You don't have to pure memorize. You just look at how many more they would need to have a full shell. For hydrogen, it's just one because the first shell is filled with only 2 electrons. That's represented by the fact that row 1 only has hydrogen and helium. And then the other atoms will be filled with 8, and so they get those by creating a bond. They get an extra electron. So carbon will want to make 4 bonds to have 4 more to have 8. Nitrogen will want to make 3 bonds to have 3 more. Oxygen would make 2 bonds. Fluorine would make 1, and the noble gases generally don't bond very often. They can be forced to bond, but we won't really have to think too much about that in OChem. And so if we remember that nitrogen has 3 bonds and then hydrogen only makes 1, we can almost immediately get to this structure, knowing that nitrogen makes 3 bonds and has 1 lone pair. So what if we got something a little bit more complicated? C2H2. Again, if we were doing this in Chem, what we'd do is we'd say, okay, we've got C2H2. We're going to count up the valence electrons. We got 2 carbons. We got 2 hydrogens. Okay, and so each carbon being in group 4 has 4. Hydrogen being in group 1 has 1. And so we count the valence electrons. We get 8 from the 2 carbons. We get 2 from the 2 hydrogens for a total of 10. And then we would begin drawing a skeleton structure. We would draw the carbon in the middle, probably, and where we draw the hydrogens, we might have to guess at that. But a good start is always just evenly distributing them, because what we want to think here is we know carbon needs to get to 4 bonds, right? Carbon makes 4 bonds. Well, when it comes to valence electrons, we've only got 10 total, and 6 are already down. So we only have 4 more we can put. And so this is a situation where we run out of electrons, and we can't give all the carbons an octet, or 8 around them, 8 electrons. They only have 2, 4, 6. And so when that happens, in Chem, what you would do is you would break out your eraser, and so we go down here, we go to our eraser, and we'd erase a lone pair. In this case, we're going to actually have to erase another one so that we can draw a triple bond, and that gives each carbon 4 bonds, 1, 2, 3, 4, and so that's the number of bonds generally carbons makes. And it's also got an octet, 2, 4, 6, 8. The hydrogen have their 2 electrons, just their 1 bond there, and that's it. So we're going to have other simpler ways of getting to this, though, that you'll learn as we start to go further into the chapters in OChem. And for example, here, just to give you a brief preview, we could compare this molecule to another molecule with 2 carbons that is called ethane. We're going to learn about that later. And in ethane, you can see that ethane is C2, 2 carbons, H6, and the molecule that we were interested in was C2H2, and so you can see the difference is 4 hydrogens, and so going from here to here, we're minus 4 hydrogens, and so each 2 hydrogens is going to be called, and we'll cover this later. This is kind of a preview, but it's called a degree of unsaturation, or DOU. And a degree of unsaturation can be degrees of unsaturation can be a ring in the structure for reasons we'll see later. It can be a double bond, is 1 degree of unsaturation, or a triple bond is 2 DOUs. So 2 DOUs for a triple bond. You don't have to know this just yet, but what I could see here is that with C2H2 there were 2 degrees of unsaturation. So that was a hint to me that we'd have a triple bond. So as we move forward, we'll have simpler organic ways of drawing the Lewis structures, but you can still always do it the old way that you did in GChem too, with counting the valence electrons. It just becomes more cumbersome as the molecules get bigger, as they will do in this class. Now, one idea that's going to be really important that you should have learned in Chem 150 is the idea of formal charge. And so formal charge is a way of, it's kind of like a good bookkeeping method of keeping track of where the electrons are in a molecule relative to where they might be in other situations. And so what we do is, and so what we're trying to look for is essentially a unbalanced charge, or a portion of the molecule that has a partial charge due to a greater than normal number of electrons or a lesser than normal number. Now, what does the normal number mean? Well, the normal number of electrons, if we're evenly splitting them between all atoms, should be the same as the number of valence electrons. So if we're splitting the electrons evenly between all atoms and all bonds, and a atom has more than its normal number of valence electrons around it in this formal charge counting method, we would say that it has a negative formal charge, too many electrons. If it has too few, we would say it has a positive formal charge. It's important to remember that formal charge is not anything real. I mean, it does have a real impact in that if electrons are more in one place in a molecule, that place will be more negative, for example. But it's just a way of figuring out what that is. And so it's different than other countings of atoms. It's different than counting for an octet. When you count for an octet, you count all the electrons around an atom. When we count formal charge, we're going to be splitting all the electrons in a bond and giving one of the electrons in each bond to one atom and one of the electrons in each bond to the other for the purposes of counting. So here's an example. Let's say we have this molecule here. What we would do is do what we see in this picture. And so the way I picture it in my mind is I take each bond and I split the number of electrons in it. So kind of like what you see here if you were creating them separate. And I just do this in my head, and then I circle each one like this and say, what is the number of electrons in each atom's circle? And is that equal to the number of valence electrons? So for hydrogen, its number of valence electrons is 1, since it's in group 1. So all of these hydrogens have 1 in their little circle, and so that's fine. That is 0 formal charge. The carbon is in group number 4. It would normally have 4 valence electrons. It has 4 electrons in this circle here, and so I would say that it has 0 formal charge. Now, oxygen, on the other hand, is from group 6 of the periodic table. However, if we count its dots in this formal charge counting method, we have 7 dots. Okay, so we have, so technically what we would do, we would say the normal number of electrons was 6, but we have 7 negatives. So we say minus 7, the 7 electrons, 6 valence electrons minus 7 formal charge electrons. And so that's going to give us a -1 or a -1 charge. And so we would indicate that on these structures by writing a negative sign in a circle, like that way. So we say that this oxygen here has a formal charge of -1. And that formal charge will affect the way that it reacts. It will, in fact, make it highly reactive with anything that's positive because it's so negative around this oxygen. And so that's the reason why we're going to be so interested in determining formal charge. It's because it's going to be really important for showing how it is that molecules will react. And so this slide goes on to describe what I just said. Oxygen should have 6 valence electrons because it's in group 6. It has 8 valence electrons, but we count 7 for its formal charge. So remember, counting formal charge is not real. It's just a way of keeping track of where the electrons are. So only 7 count till its formal charge. So since it has 7, but it should only have 6, it has 1 more electron than it should have, at least in terms of this kind of fake-ish formal charge counting method. And so we would say that it has a -1 formal charge. And you'll get good at this over time. You'll be able to spot it really quickly the more you do it. But practice at that. Practice for looking out for formal charge. You'll notice that an atom will have a formal charge generally when it's not making the correct number of bonds. So oxygen here normally makes 2 bonds because it's in group 6, but it's only making 1, and that's why it has a formal charge. However, carbon generally makes 4 bonds, and it is making 4 bonds, so it has no formal charge. So that's a quick way of checking to see, should I even be looking for formal charge? But once you spot an atom not making its normal number of bonds, that's a pretty good indication that there's going to be a formal charge there. Not always, but it's often the case. So you want to check. When it comes to covalent bonds, we can describe them as either polar or nonpolar. So in nonpolar, and remember, covalent bonds are bonds between nonmetal atoms generally. So these are the bonds we're going to be most interested in organic chemistry, covalent bonds. And so we want to describe them as either nonpolar or polar. So in a nonpolar covalent bonds, the bonded atoms are shared evenly between 2 electrons. So you'll have a perfectly nonpolar bond if you have, for example, hydrogen bonded to hydrogen, because hydrogen is the same atom as hydrogen. So neither of these atoms will be pulling on the electrons more in one direction than in the other. A polar covalent bond will be between atoms that have very differing levels of pull on their electrons in the atom. For example, a great example is oxygen bonded to hydrogen, like in water. And in fact, if you look at the geometry of water, as we soon will, we'll find that it has a kind of bent geometry like this, which we can kind of try to show by the way we draw the Lewis structure. But it's important to note that both of these Lewis structures are correct. Lewis structure does not necessarily tell you the geometry of the molecule. You have to determine that. But anyway, in this hydrogen-oxygen bond here, the oxygen has a electronegativity of 3.5. Electronegativity is a measurement of how strongly an atom attracts the electrons that are shared in a bond with another atom. So hydrogen is electronegativity of 2.1. You can see that electronegativity is very high at the top right of the periodic table and gets lower as you go down to the left. High pull on electrons is what gives nonmetals their property. They hang on to their electrons very tightly compared to metals, and more tightly as you talk about atoms more to the top right of the periodic table, especially fluorine, the highest in electronegativity. But we look at the difference here, and if we see if this difference is 0.5 or greater, so electronegativity difference 0.5 or greater is considered is a polar bond. Now, if there's an electronegativity that's lower, really what that just means is that it's less polar, right? But for simplification purposes, we often say that when the electronegativity difference is getting 0.5 or greater between 2 atoms in a bond, that is a pretty polar bond. If it has 0.4 difference, is it completely nonpolar? No, it has some polarity, but it's getting small enough that we say it's not very significant. So here, the electronegativity difference, 3.5 minus 2.1, that is 1.4. And oxygen has the much higher electronegativity. So what we can see here is that in a water molecule, the electrons will be pulled towards the oxygen atom, and depending on the shape of the molecule, that will have consequences for the polarity of the entire molecule. Um, and so here's another example of various bonds. Carbon bond would be not polar at all because they have exactly the same electronegativity or pull on their electrons. However, a carbon-oxygen bond will be more negative on the oxygen side than it is on the carbon side, assuming that there's nothing else in the molecule to pull electrons in an opposing direction. When you have an extremely polar bond, it's no longer really called a covalent bond, it's called an ionic bond. And that's referenced here by the way that the lithium is written here with a plus charge. The carbon, in this case, has an additional electron that it's taken from the lithium, and therefore it has a negative charge. And so it's important to note that covalent and are polar and nonpolar are not a dark sharp line. They are a continuum like this. So we say that a carbon bond is completely nonpolar, so it's the most covalent of bonds. And then in between covalent and ionic, there are polar covalents. So this happens when we have greater and greater differences in electronegativity. When the difference is great enough, at that point the nonmetal atom will simply steal the electron from the metal atom, and that's what's referred to as an ionic bond, when the nonmetal completely takes the electron from the metal. So in this class, or in general chemistry, when you wrote Lewis structures, you generally wrote them like this. So this is amoxicillin, a kind of antibiotic, and you can see that the structure is quite complex. And so in organic chemistry, we end up drawing large structures all the time. And so what we want to do is have a simpler way of drawing them, and that is the so-called bond line structure, as you can see here on the right. So there are certain things that are different about the bond line structures than about the traditional Lewis structures that we used to draw in Chem that have all of the atoms, all of the lone pairs. First of all, you'll notice the lone pairs are gone. And this is where it becomes useful again to know how many bonds an atom generally makes. To know that carbon generally makes 4 bonds is useful here. All these carbons are making 4 bonds. To know that nitrogen makes 3 bonds and has 1 lone pair, usually, unless it has a formal charge, that's useful because you're going to see that all over the place. And so that helps you to say, oh, look, this nitrogen here is making 3 bonds, 2 to hydrogen, and then this one on the bottom here is to carbon. So this would be a carbon atom right here. And so you can see it fully drawn right here. So this nitrogen is attached to 1 carbon and 2 hydrogens. That's 3 bonds. And so the other electrons that are missing to give it 8 are the lone pair. And so you can, once you get more comfortable with reading these bond line structures, you can do that very quickly just by scanning the structure. And so that makes it a lot easier to write bond line structures because we don't have to use all of these lone pairs, which take a long time to put down. Another example here you can see is oxygen in 2 situations. So this oxygen is making 2 bonds and has 2 lone pairs, but one of those bonds is to carbon and one is to hydrogen. And notice we often don't draw the line between the oxygen and the hydrogen either. Sometimes not between the nitrogen and hydrogen either in the line structure. Right here you can see an oxygen that's making 2 bonds as well, except those 2 bonds are a double bond to the carbon. But still, the oxygen is making 2 bonds and 2 lone pairs. So remembering that nitrogen is 3 bonds and 1 lone pair, carbon is 4 bonds, sulfur and oxygen are both 2 bonds and 2 lone pairs. That's really, really useful, and you'll remember that pretty quickly, just because you're going to be using it so very often. And so this allows you to quickly fill in lone pairs in your mind. Oh, this oxygen is making 2 bonds, it has 2 lone pairs. Or this sulfur is making 2 bonds, it has 2 lone pairs. This nitrogen is making 3 bonds, it has 1 lone pair, and so forth. This oxygen is making 2 bonds. It has 2 lone pairs. So you can fill these in your mind once you're starting to get used to these structures, and you don't have to draw them anymore because everyone knows. For carbon, there's usually so many carbons in an organic molecule, we don't write them out. Carbon is represented in 2 ways. So I'll go to the next slide for that. So in a bond line structure, we draw them in a zigzag format, and each endpoint represents a carbon atom, and each zigzag represents a carbon atom. So going back to our amoxicillin structure, sorry, my cat again. Boy. Going back to our amoxicillin structure, if you take a look, if we look at this carbon right here, that's this point right here. Okay, so each of these is a carbon right here, 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 here. And then each carbon here, or each endpoint, like this one here, is also a carbon. So this endpoint is this carbon right here. And notice lastly, hydrogens that are attached to carbons are not drawn. Why? Well, it's because we all know that carbon's going to make 4 bonds. Never 3, never 5, always 4. So whatever bonds are not shown are hydrogens. So right here, there's only 1 bond to 1 carbon shown. So we can fill in our mind that there must be 3 hydrogens, because that will give this carbon 4 bonds. For this carbon right here, it's making a double bond. So this one right here, it's making a double bond. It's making a single bond here, and then it's making another single bond. So that's 4 bonds already. So we know that it has no hydrogens attached. However, this carbon right here, it's making 2 bonds to this carbon, 1 bond to this carbon. So that's only 3 bonds. So it must have 1 hydrogen attached. And so that's going to be the quickie way we use to draw structures in organic class, this bond line structure method. So here we can see here we have several bond line structures, and again, each endpoint is a carbon and each zigzag is a carbon. So in terms of carbons, we got 1, 2, 3, 4, 5, 6 here. So we could write that in standard expanded structures like this: 1, 2, 3, 4, 5, 6. And then we need to give each carbon 4 bonds. So this carbon has 1. So the remaining bonds, if nothing is written, are all hydrogen. So this is hydrogen here. And then this one will be 2 hydrogens. And we can even condense that further and just say, oh, this carbon, like this one, has 2 hydrogens attached. So we can say CH2. This carbon has 2 bonds to carbon, so it must have 2 bonds to hydrogen. This bond has 2 bonds to carbon, so it must have 2 bonds to hydrogen. This one only has 1 bond to carbon, so it has 3 bonds to hydrogen. So we could even draw these out here if we wanted to. So you can do this at first as you're getting used to reading these bond line structures, for example, in the Chapter 1 homework this week. So you can say, oh yeah, this carbon's only making 1 bond to carbon. It must have 3 hydrogens to have 4 bonds total. This one is bonded to 2 carbons, so it must have 2 hydrogens. This one's bonded to 2 carbons, so it must have 2 hydrogens, and so forth. So you can fill in the hydrogens until you get comfortable with the bond line structures. But after a while, you'll be reading them over and over, and you'll get more comfortable. Now this carbon right here, you can pause the video if you like. How many hydrogens are on each of these carbons in the second molecule here? So pause if you want to take some time to figure that out on your paper. I encourage you to try the rest of these, in fact. Make sure to give every carbon 4 bonds. Okay, perhaps you've unpaused now. So this carbon only making 1 bond to carbon, so it has 3 hydrogens. Oops. 3 bonds 3 bonds to hydrogen. This one, however, is already bonded to 3 carbons, so it only has 1 hydrogen. This one has 3. This one right here has 2 bonds to carbon, so it only has 2 hydrogens. This one as well, 2 hydrogens. And I'm just going to draw the little red lines out to represent the hydrogens. So these are the hydrogens. So I'll put that one. Okay. Here, this would be 3 because it's only making 1 bond, this carbon. But this carbon right here is making 3 bonds. The next one, 2 to 1 carbon and 1 to the other. And so since it already has 3 bonds, it only needs 1 hydrogen. Same thing for this one here. And then this one needs 3. And this carbon at the end also needs 3. So this is a carbon with 3 hydrogens attached. And also the one at the other end has 3 hydrogens attached because this carbon is only bonded to 1 carbon right here. This is a carbon, this is a carbon. And these carbons right here have 4 bonds. This carbon has 3 bonds, a triple bond to this one, and 1 bond to the other. That is 4 bonds. So no more hydrogens should be attached there. So you can see how this is a simplified and quicker way of drawing Lewis structures compared to the way you used to do it in G-Chem. And that's the way we're going to start doing it more and more in O-Chem. And so here's another example where the hydrogens have been filled in. So you can see the oxygen, it's already making its 2 bonds with its 2 lone pairs. It's fine. That's going to be shown. What's not shown is the number of hydrogens attached to the carbon. Again, this carbon here making only 1 bond to this carbon underneath the oxygen. And so it has 3 hydrogens attached. This carbon here is making 4 bonds. 1 to this carbon, 1 to this carbon, and then 2 to oxygen. So that's 4 total. It doesn't need any more bonds. It has no hydrogens attached. This carbon here making 2 bonds to carbon, 1 here, so it needs 2 hydrogens attached. This carbon making bonds to 2 carbons, 1 to the left, 1 to the right. It has 2 hydrogens attached. This carbon has only 1 bond to a carbon, so it needs 3 more bonds to have 4. So that's 4 hydrogens attached there. Finally, let's begin to talk about atomic orbitals. So again, the focus here, as you've probably noticed as we're talking about this, is where are the electrons at? Are they in the bonds? Are they in the lone pairs? We're drawing Lewis structures to see where those electrons are. Now, in atoms, in bonding, there are 2 ways to describe, 2 main theories for describing bonding. The valence bond theory and the molecular orbital theory. And the valence bond theory begins with the idea of atomic orbitals. So electrons in an atom, so atomic, before they're molecules, but sometimes in molecules as well. They have electrons that are contained in certain areas where they're likely to be. So in the 1920s, quantum mechanics was established, and it established the wave property of electrons, which meant that electrons behave both as a particle or as a piece, but also have a wave. And so we have wave equations that describe the likely locations for an electron. And those likely locations are can be plotted to a graph and exhibited with pictures here that we call orbitals. So the type of orbital will be identified by its shape. For example, spherical orbitals are called s orbitals. The orbital is describing a region where the electron is 90% probability of being inside this area. And then the probability quickly tapers off as you move farther away from the nucleus. So one of the central tenets of quantum mechanics is that small things, and even large things, but especially small things in a way that can be observed, behave as waves. And so the wave is described by a so-called wave function, and you can compare it to waves in a lake. And so those electrons are spread out over a certain area, a wave as a wave, and the wave can have positive peaks and negative valleys. And the interface here between a peak and a valley is called a node. And these waves, when they're added together, they amplify in certain regions and they are diminished in others. And so they're very diminished, for example, in the node between two lobes. This drawing here is a representation of a p orbital. So s orbitals are spherical in shape. The electron can be evenly in any location around the nucleus. P orbitals are dumbbell shaped, and so they have directionality to them. And so when we have p orbitals like this, when bonding occurs according to valence bond theory, it will occur due to the overlap of atomic orbitals, such as s and p orbitals like this. And so the node here is representing the interface between the wave function, where the wave function can be described as neither positive nor negative, and it's described as positive on one side and negative on another. And now this is a very quick cursory overview of quantum mechanics. You went into a little bit more detail in G-Chem, but what's most important is to understand the shapes of these atomic orbitals in O-Chem and how they might interact and overlap with one another. So when we have an s orbital is composed of a single orbital that can contain 2 electrons. A set of p orbitals come in 3 degenerate or equal energy types in one energy level in an atom. For example, in the second energy level of an atom, it includes p orbitals, and those p orbitals come in a set of 3 that are all positioned with their lobes perpendicular to one another. Here we have the lobes in the y direction, the lobes in the x direction, 90 degrees are perpendicular to the y direction, and then lobes in the z direction, which is also perpendicular to those. So electrons occupy so-called atomic orbitals in atoms, and those orbitals always follow a particular pattern of energy and relative energies, with the lowest being the so-called 1s. So the 1 being the principal quantum number or the energy level that the electron is residing in and around an atom, and the s being the type of orbital. Now the first principal quantum number, the first energy level, is closest to the center of the atom. Then the second is further out, and the third is further out, and so forth. We're really only going to be involving ourselves mostly with the 1s, the 2s, and the 2p orbitals. We don't need to go into all the detail that we went into in G-Chem, but they fill in this fashion. If you forget, well, what are the what's the lowest energy orbital? What's the next lowest? So lowest is called 1s. The next energy level above that is called 2s, so it's spherical in shape in the second energy level around an atom. The next higher is 2p. Now, if we go here to our periodic table, which I'm going to bring up right now, Chem 212, rep. Just a second. I should have brought this up earlier. Okay. We take a look at the periodic table here. What we'll see is that the first energy level is represented by the first row. And helium, for the purpose of this, kind of belongs right here. We put it right here as well, the helium. So this region, the first 2 columns, represents electrons going into the s orbital. So the lowest energy orbital is the 1s. It is filled with 2 electrons, represented here by the hydrogen and the helium. The next lowest energy level is the 2s, represented by the lithium and the beryllium here. Then the next higher energy level is the 2p, which is represented by this region here with boron, carbon, nitrogen, oxygen, fluorine, and neon. Notice that here we're filling up p orbitals, and p orbitals come in sets of 3, which can each fit 2 electrons. So 3 p orbitals with 2 electrons, that's 6 total. And that's why this region here, where the electrons are going into p orbitals, is 6 across. So you can see that that's represented by these as well, the 1s orbital being the lowest in energy. Then the first electron, hydrogen only has 1 going there. For helium, the first and second electron going into the 1s. Then at that point, with lithium, we would go down to the second row, so we'd be filling the 2s. Lithium has 1 electron in the 2s. Beryllium has 2, so you can see that right here with lithium and beryllium. And then boron here is going to be the first element that has an electron in its p orbital in the ground state. And so you can see here we're in the second row still, but we're in the p region. The first one is boron, so it has 1 electron in its 2p orbital. Carbon has 2, nitrogen has 3, and oxygen has 6. An important note is that these electrons fill up the p orbitals one at a time, since they're equal in energy, until each one has 1 electron. Then you can see with oxygen, which has 4 electrons in the 4p, that electron pairs up. So in valence bond theory, well, actually, I'm going to stop this video this time. I'm going to make one more video about the same length, maybe a little less, about half an hour. And that will be the second and final lecture video for this week. And so that will constitute together about an entire lecture period in our class. So I hope to see you, or please come back. You should watch the first video on Wednesday, the second one no later than Thursday, I'd say, certainly by Friday. So I'll see you for the next video.